All right, this is going to be the final video in our series of nucleophilic additions to aldehydes and ketones. So the last one I want to cover is the addition of alcohols to aldehydes and ketones. So this is a very important reaction for what we call installing protecting groups and also in synthesizing polysaccharide molecules that we'll see later in our carbohydrates discussion. But we're just going to start with the basics right now and look at how we add alcohols to aldehydes or ketones. So I'm going to start with a generic ketone. All right, so this will be a methyl ketone. And then what I need to do, much like in the addition of the amines, I need acid catalyst here. All right, so the alcohol itself is not nucleophilic enough to add to the ketone. So what I need to do is get that ketone activated by adding an acid. So in our first step, we're going to see protonation of the carbonyl group, all right, with H3O+, and this is a reversible reaction. And we're going to then have an activated ketone and at this point water could attack, but if you had a large excess of alcohol in solution like methanol, you could favor the reaction going forward with the alcohol attacking, and that's what we'll do. We'll end up using a catalytic amount of acid, all right, and then have our alcohol essentially be the solvent, so we can guarantee almost exclusive attack by the methanol in the subsequent step. So as we've seen again and again, we're having nucleophilic attack of the carbonyl group. In this case, it's activated by being protonated. So we attack that carbonyl carbon, and much like in the case we saw with the addition of amines, we get something called a tetrahedral intermediate. And in order for this tetrahedral intermediate to collapse, we are going to need a group to leave. All right, so one of the oxygen atoms is going to kick in, and then a group will leave, but the only group that can leave off a tetrahedral intermediate in acidic solution is one that is protonated. And in this case, the group we just attached is protonated, so we actually need to transfer that proton. All right, so what I'm going to do is flip the page and redraw our tetrahedral intermediate that we have and show how we're going to transfer that proton. Oops, it's protonated. This oxygen was not, and we had a methyl group here. And we had water left over from the first step, and it will actually do our proton shuttling for us. All right, so we remove the proton from the alkoxy group, and now we have hydronium. And what's going to happen here is we are either going to kick off our OH group, or we can actually stop here if we're very, very careful. All right, so we're going to look at this product and call it something. And what this thing is called here is something called a hemiacetal. All right, so this is an important intermediate, especially in carbohydrate chemistry. All right, what a hemiacetal is it's going to be a tetrahedral intermediate where one of the groups is an alkoxy group. All right, so I'm going to point to the alkoxy group in red. So this is what we call alkoxy. And then, of course, we have hydroxy. So when we have both the alkoxy and hydroxy attached to an sp3 carbon, which I just highlighted in red there, we would call this thing a hemiacetal. All right. So hemiacetals actually are very hard to isolate in this sort of chemistry. So what we're actually going to see is the hemiacetal continues to react. All right. So the way that is going to happen is that we are going to protonate this hemiacetal by the hydronium that is swimming around in solution. So we protonate that group. Have our alkoxy group here still. And the alkoxy group is actually going to kick in and throw out the water. So now what we're going to get is the collapsed intermediate here. So this is no longer a tetrahedral intermediate. But if you remember what I said before, we're going to have a very large excess of alcohol in solution, in this case methanol, our solvent. And that does not look like an oxygen atom. I apologize. Let me try this again. Much better. All right. So this guy's already activated. So it's going to get attacked. And what I'm going to do is move to the next slide where I'm going to show the new tetrahedral intermediate here. All right, so here's our new tetrahedral intermediate. And if you remember what I said before, the only way a group can leave is if it's protonated. All right, so we can either shuttle the proton onto the other oxygen-containing group and really just go back to where we were, or water in this case, can actually remove the proton here, and we kind of come to a stopping point if we bias the reaction conditions just right. All right, so if we go back to here, this guy was called a hemiacetal. And the way you recognize the hemiacetal is the alkoxy group and the hydroxy group. This guy has both the oxygens in what we call the alkoxy form. So we have both of these groups I've pointed to in red are alkoxy. Ooh, goodness. Alkoxy. Right. So both of those groups are alkoxy. So this is not the hemiacetal, but this guy will be called the full acetal. All right. So we have an acetal and a hemiacetal. So let's kind of recap what those look like here. So the general format for a hemiacetal is the following. All right. So how do you identify this? It's an sp3 carbon, one group here and one group there containing oxygen. Both groups, contain oxygen. One is hydroxy and the other is alkoxy. To identify the acetal, your oxygen groups will now be both alkoxy. All right, so this makes what they call the acetal. So an old joke that a professor told me once is that you have the full acetal and the hemiacetal, and they said, well, why didn't they call it a half acetal? Well, half-ass and, just sounds weird. So you have the hemiacetal and the acetal. All right, so let's summarize the reaction here. We're going to take a ketone, and in this case we're going to go back to acetophenone. And what we're going to need is going to be H3O plus, and this is catalytic, so I'll put in parentheses cat, and then we're going to need an alcohol. All right, in this case I'm going to use ethanol, and this is often ran with a large excess, all right, or a solvent as our ethanol. All right, so what we're going to do is we're going to make the acetal. Making the hemiacetal is extremely difficult under these reaction conditions, so for the most part just be able to identify making the full acetal. All right, so there is the skeleton of our acetal, and now we just need to figure out what R groups got attached, and they're right here. All right, so it's the ethyl group. So this would be CH2, CH3, and over here we have CH, oh goodness, start writing please, CH3, CH2. All right, there we go. So there's our two R groups. And this is making, of course, the acetal. All right. You can get really creative with this reaction, and let's go back to acetophenone. And I'm going to use, instead of an alcohol, we still need our catalytic amount of hydronium here, but rather than using the ethanol or an alcohol, I'm going to use something called a diol. And this diol here is known as propylene glycol. All right, so a diol, of course, is a molecule with two OH groups, but this is pretty cool because each one of these OH groups is going to attack the carbonyl carbon in succession. All right, so it's going to be an intramolecular reaction. So once this guy attacks, then there is a built-in nucleophile on the other end that can come around and make a new ring system. All right, so the way this is going to work is the same approach. However, since we have an intramolecular reaction, because intramolecular reactions happen so much quicker than intermolecular reactions, if we count these carbons, 1, 2, 3, those are the carbons that are going to be attached. So we're going to have carbons 1, 2, and 3 right there. So there they are, 1, 2, and 3. Now, you make these cyclic acetals, and this only occurs if you're using a diol. All right, so if we go back and look here, if we're using just a simple alcohol, you're not going to get the cyclic acetal. But if you use a diol, you'll get what we call the cyclic acetal. All right, so that is pretty much the addition of alcohols to aldehydes and ketones, and that's going to complete our modules or videos, I guess, for chapter 21. Right, so there's a quiz up on D2L that you could need to download and send in via photograph, and then drop that into the Dropbox. Of course, sign the pledge there, and we'll catch back up soon on a new set of videos for our subsequent chapter. So thank you very much, and I hope everybody's doing well, and please reach out to me if you need anything. Thank you very much.